So the Fragile Families Challenge is a scientific mass collaboration that I've been working on with my co-organizers, Ian Lundberg, Alex Kindle, and Sarah McClanahan, and it has involved hundreds of people around the world, some of whom are in this room. Thank you. Some of whom are on the live stream. Thank you. So how many of you have participated in the Fragile Families Challenge? Great. Okay. So let me tell you about what this is. So as you heard before, I love Wikipedia. And to me, this idea, the example of Wikipedia makes me really wonder, like, what is it that we can do together? And the idea of mass collaborations in science is not new. So this is the paper announcing the sequencing of the human genome. This paper had about 200 authors. This is the paper announcing the discovery of the Higgs boson. This paper had 5,000 authors. Working together from all over the world. So these are their institutions. So if hundreds of biologists working together can sequence the human genome and thousands of physicists working together can find the Higgs boson, what would happen if we had hundreds of social scientists and data scientists collaborating on a project? What would that look like? What could we all do together that none of us could do individually? And that's the Fragile Families Challenge. So that's the sort of methodological introduction to the Fragile Families Challenge. Now let me give you a more substantive introduction in terms of the research that I see in sociology and the social sciences. So in the social sciences, there's often there's a field called stratification, which is generally concerned with social inequality. And so if I had to summarize, this is a huge part of sociology, and if I had to summarize this entire field with an equation, it would be this one. So let me just summarize this quickly. We have some outcome that we call attainment. This is generally like what happens to someone. So this could be, do they graduate from high school? Do they graduate from college? What occupation do they have? What income do they have? That's kind of the outcome, the attainment. Then we have some predictable component of attainment. We usually model that in terms of a regression. So then we have some unpredictable component. So this is the error term in our regression models. This is the part that we usually don't talk about. This is the part that we ignore. So we all focus tremendously on this predictable component, and we ignore the unpredictable component, and that leads to this paradox that most of our attention and theorizing is focusing on the predictable component, but empirically the unpredictable component dominates. In fact, the unpredictable component is so big, like how often have you seen R-squareds published about regression, individual level regressions, R-squareds of like 0.05. Let me just summarize what that means. If you did a scatter plot, it would look like a big cloud. This is like most of what is happening is not captured by your model. But yet we continue to talk about what is in the model. So what would happen? Now, there are a lot of possible reasons why the unpredictable component seems to be dominant in empirical research, even though we don't pay attention to it. So one possibility is, well, we're not really focused on making the best possible prediction. So when people build these models in stratification, they would say they're trying to explain things or understand things. They're not trying to make predictions. So let's say, well, what if we were trying to make predictions? How well could we do it? And how well could we do it if we had a very large, what social scientists consider to be very large and high quality data source? And what if we used methods that were specifically focused on predictive performance? So this is another thing, is social scientists will say, well, I'm using linear regression because that produces more interpretable results. I think interpretable is a loaded term here. But So what if we say, you know what, let's just give up on that. Let's use whatever method you want from machine learning. Let's get a huge data source, and let's see how well we can do with these predictions. And so how small can we get this unpredictable component to be? So I do want to say like why I think we should care about the predictability of social outcomes, because sometimes when I talk about this, other people say, well, I just don't even care. Predictability is not what we do. Like, we're not trying to be weather forecasters. So I would say, first, I actually like weather forecast. I mean, I think it's a useful thing. And weather forecasting is a good way for meteorologists to know if they actually are able to, how much of the system they are studying they actually can predict about. And it's also then very useful for generating new theories and figuring out what kind of new data would be useful. So if you continually screw up certain kinds of weather forecasts, then you might say, oh, well, we seem to be doing really bad on cold days. I wonder why that is. And that's actually generative for thinking about new mechanisms and new data. So I think we should care about predictability of social outcomes for scientific reasons. So first is, I think it's a basic social fact. So in the social sciences, we've spent a lot of time trying to study the relationship between a parent's occupation and their children's occupation, or more generally, a parent's background and their child's outcomes. This is a huge area of study. This is often described as a descriptive problem. We're going to describe the patterns. But it could also be expressed as a predictive problem. Given certain data about parents, how well can I predict what will happen to their kids? Given certain data about the parents and the kids up to a certain age, how well can I predict what will happen to the kids at future ages, right? That answer depends on what data we have, depends on what time we are in society. So that predictability might be different in 1800 in the US and 1900 and 2000. And it also varies a lot by country. So these are basic social facts that we would like to know. The second is the desire to improve predictive performance can lead to new kinds of discoveries. As I gave an example in the weather setting, if we seem to be failing at our predictions at certain kinds of outcomes or certain kinds of families, that might lead us to realize that there's things that we haven't been considering. It might also lead to methodological development. And then lastly, for policy reasons. So this is an article from the New York Times Magazine about whether an algorithm can tell whether kids are in danger. This is describing what's happening in Allegheny County, Pennsylvania. So there, the Child Protective Services are using algorithms to help make decisions about which cases to investigate. So let me briefly describe what happens. So in Allegheny County and many other areas in the US, there's a number that you can call if you think there's a child in danger. So the person answering that phone has to decide whether to investigate the call or not. And this is a very difficult decision, and obviously you don't want to get it wrong. So if the child is in danger, you really do want to go and investigate. If the child is not in danger, you actually do not want to investigate, because these investigations are very disruptive to these families. So you really want to make the right decision. And so what they've done in Allegheny County is they've taken all the administrative data that the county has, and they've taken, then they've built a machine learning model on this administrative data, which produces a risk score for each family. And then when there's a call, the person who has to decide to do the investigation or not also has access to this risk score. So the algorithm does not make the decision, but it assists the human in making the decision. And so some people find this very, very deeply scary and deeply troubling. So they say, if this algorithm is trained on historical data, then we are potentially just reproducing all the biases that have existed in the past. So in the same way we have this expression, garbage in, garbage out, it is also the case that if you have bias in, you have bias out. So On the other hand, other people say, yeah, these systems have been really terrible for many years, and this is a chance that we can actually try to help make them better. Humans are biased, and so if we build in these more data-driven approaches, we can potentially undo some of these biases. So I personally am deeply conflicted between both of these views of the exact same problem. But what I do think is that as the policymakers who are grappling with these decisions, they need some basic facts about how predictable outcomes are with what kinds of data. And so one of the reasons why, as scientists, we should be interested in this is the people who have to make these decisions need basic scientific facts to make them wisely. So the data set that we are going to use is the Fragile Family and Child Wellbeing Study that my colleague Sarah McClanahan has been running along with others for the last 20 years. So it's a birth cohort study. So they sampled about 5,000 children who were born in 20 US cities with an oversample of non-marital births. So this study was designed to understand children who are born into families where the parents aren't married, to understand what happens to these families over time and what happens to these children. So the name of the study, The Fragile Families, is both acknowledging that these are families, even if the parents aren't necessarily married, and that these are fragile families. These are the families that often don't stay together. So they followed these families over time from birth through the time that the kid is age 15, and this data has been used in hundreds of papers and dozens of dissertations. So this is the way a social scientist might look at this data set. So each row here is a module of data collection, and each column is a time. So at birth, for example, they interviewed the mother and the father. At age 1, they interviewed the mother and the father, and you can see that as the kid gets older, the range of data collection increases to include also an in-home visit, a survey with the child, survey with the teacher, survey with the child care center, and so on. So then when we started the Fragile Families Challenge, the world looked like this. So Sarah and her colleagues had collected the year 15 data. It was on their computer, but it was not yet publicly available. And this happens all the time in longitudinal surveys. There's a period of time where the data is collected, is being cleaned and prepared for public release, but it is not yet available. And this routine part of the process is a magical opportunity for research. When something like this happens, this is magic, and it is a great opportunity that we could be taking advantage of. And so this is the way a social scientist might think about it, and then this is the way a data scientist might think about it, the exact same data, and this will explain what this magical opportunity is. So we have a big matrix. We have 5,000 families, and then we have 12,000 features or variables. So if you stitch together all of the data that has been collected over the years about these families, it is an enormous amount. I would say a relatively small number of these variables are ever actually used, and the rest are kind of just sitting there. And I want to also highlight the shape of this. So this is data where there are more features or variables than there are people. So this is sometimes called high-dimensional data. So this comes up a lot in machine learning and data science. Social scientists often think of themselves as being in a different world where you have potentially more people than variables. But I think actually oftentimes social scientists are in this high-dimensional world, but they just never think about all the variables that they have. So here we have this high-dimensional data set, and we have a bunch of outcomes at age 15 about the kids and the families. So what we did is we picked 6 outcomes, and then we split the data into 3 parts. We have a training data set, which is half of the outcomes that we made available to participants in the challenge. We have a leaderboard set, which people can query while the challenge is going. And we have a holdout set that we keep until the end. So this structure is a very common structure that you'll see in machine learning. It's called the common task method. So basically, everyone agrees on what the data is. Like, there's a common task. There's a common metric, mean squared error, And then there's holdout data at the end that no one has access to. And so you can see this has similarities to the kinds of open calls that I described. So I don't know what is the best way to predict what is in that holdout set. I have no idea. But anyone can participate and try to predict what's in the holdout set. And then I can calculate the mean squared error and see who did the best. So by making this a problem where its solutions are very easy to check, it enables us to be much more open to participation from all kinds of people. So we can get people who aren't normally participating in this kind of research, and they can bring new ideas about how to potentially approach this problem. So the 6 outcomes, there are 2 that are a property of the kid. So the GPA of the kid, which is continuous. This is the grades in school. The grit of the kid, which is a psychological measure that's similar to perseverance. There are 2 measures of the household: eviction, which is whether the family was kicked out of their house; material hardship, which is a measure of experienced poverty. So poverty is defined by your income. Material hardship is defined by your experiences. So for example, material hardship includes questions like, I went to bed hungry. I've not been able to go to the doctor because I couldn't afford it. Those kinds of questions make up the material hardship scale. And then some of these are questions about the primary caregiver, whether they participated in a job training program or whether they lost their job. So 459 researchers applied to participate in the Fragile Families Challenge. Many of them worked in interdisciplinary teams, and the goal was to make predictions that minimize the mean squared error in the holdout set. So by mean squared error, I mean this thing here, the difference between the predictions and the truth, squared and averaged over the data in the holdout set. So I said 459 researchers applied to participate. I also want to call attention here to the privacy and ethics audit that we did. So we have a lot of the data in this study is personal, and so we went through a privacy and ethics audit deciding how to safely enable this project to happen. So there's a trade-off. Remember I said all this good stuff about new people coming in with new ideas? It's also possible that new people are coming in with bad intentions. And so in this paper, we talk about how we balance these concerns, what we did, and we're trying to be public about what we did, not because we think it is perfect, but because we want other people to be able to do it better in the future. So if you're interested in that, I'd be happy to talk more about it, and it's described in that paper. So people don't have good intuitions always about mean squared errors, so I'm going to instead talk about something else, which is the R squared of the holdout. So we're going to take the square difference between the predictions and the truth in the holdout set, and we're going to rescale that based on what you would get if you predicted the mean of the training data. So this is kind of like a very naive prediction. So if the mean GPA in the training data is 2.8, we could just predict 2.8 for everyone. That's kind of like a null model. And then we're going to take 1 minus this. So this R squared holdout ranges from 0 for something that's predicting the mean of the training data to 1, which is perfect prediction. So using a large, high-quality social science data set collected since birth and using modern machine learning methods, any methods people want, hundreds of people, what was the best submission? What was the most accurate that anyone was able to make these predictions? So before I show you, I want to vote. I want to have you all vote. So we're going to do like, I think it's called a Dutch auction. So I want you to raise your hand. How many people think the R squared is greater than 0? So you should raise your hand. Now I'm going to keep increasing the number, and I want you to keep your hand in the air until we cross the threshold where you don't think it will happen anymore, okay? So how many think the R squared is greater than 0? Every hand should be up now, unless you're really not very confident in our capabilities. Okay, greater than 0.1, greater than 0.2, greater than 0.3, greater than 0.4, greater than 0.5, greater than 0.6, greater than 0.7, greater than 0.8, greater than 0.9, 1. Okay, great. So there's a big range. There are some in the 0.2 area, and there are some all the way up to the 0.6 or 0.7, 0.8 area. So let me now show you the results for, again, this is for the best submission. So we see about 0.2 for material hardship and GPA, and I would say pretty close to 0 for the other 4 outcomes. So let me now show you this on the scale that I think is the correct scale, which is this one. So I think the dominant pattern that we see here is this vast white space. So all the things that we have thought about and measured are in the blue, and there is a lot of vast white space. So what is in that vast white space? That is what we are working on now, but I want to tell you a little bit more about these results. Is this even better than a benchmark model? So often, sometimes people will say, oh, I have this fancy machine learning thing, and we had hundreds of CPUs do a bunch of crazy things. The first question you should ask is this really actually, how does this compare to some basic, simple thing? So we gave one simple thing, is just predict the mean of the training data. That's like a super basic comparison. But let's take a simple comparison where we say a linear or logistic regression model with 4 variables. So the 4 variables would be the race, ethnicity, level of education, and marital status of the mother at birth of the kid, and then a lagged measure of the outcome at age 9. So often if you want to predict something in the future about someone, a good predictor is what they had that thing in the past. So if you have those 4 simple variables, and then you have a linear or logistic regression model, how does that do compared to this? That's the green lines. So the very best model is not qualitative. It is better than a very simple linear regression model with 4 variables, but it's not substantially better. So I want to show you what this looks like, because I think we can see r squared of 0.2, and it's hard to really know what that is. So this is a scatter plot. This is my favorite, one of my favorite measurement and scientific tools of all time, the scatter plot. So the x-axis here is the prediction. The y-axis is the truth. The one on the right is the best submission. So again, if this was working perfectly, it would all fall along the 45-degree line. You see that that's not the case. So what is that dotted vertical line? So that is the mean of the training data. So if everyone predicted just the mean of the training data, that's what they would predict for all the kids. So if your intuition is that the best model is like the truth with some noise, that's the wrong intuition. The right intuition is the best model is like the mean of the training data with a little bit of wiggle in the right direction. That's really what's happening. And then the benchmark model, that's the 4-variable linear regression model, is on the left. And you'll see that, qualitatively, those look pretty similar. So now let me show you the results for all of the continuous outcomes. So you see, again, a very similar thing, that the best model is basically the mean of the training data with a little bit of movement in the right direction. And qualitatively, the best submission and the benchmarks are very, very similar. Now I'm going to show you for the binary outcomes. So what I'm showing you on the right is the best submission. The top box is for families where an eviction occurred. The bottom box is families where an eviction did not occur. So if the best model was working really well, you would see big separation between these things. So when an eviction occurred, the predicted probabilities would be very high, and when an eviction didn't occur, the predicted probabilities would be very low. Again, the dotted line is the mean of the training data. And so what you see is that in the cases where an eviction did happen, you do see predictions slightly higher than the mean of the training data. And in the cases where an eviction did happen, you do see predictions slightly lower. But there's still not a huge difference between those panels. And then comparing again the benchmark to the best, they're again very, very similar. Here are the results for all the binary variables. Again, qualitatively the same pattern. The best submission is basically the mean of the training data with a little bit of improvement. And the difference between the best and the benchmark is very small, not visually apparent. Okay? So there I've only been focusing on the best submission. But actually, there were many, many, many submissions. 160 valid submissions we received. So not 160 valid final submissions. So people submitted many times, and then we just looked at their final submissions. So what if we look across all the submissions? What can we learn that way? So let's think about what the patterns of errors might be. So let's imagine I was going to make a heat map where I was going to have one row for each family and one column for each submission. Okay? So now, and then the square in that heat map is going to be redder if there's bigger squared error. Okay? So if we're in a world where the most important thing is which model you're using, like did you use random forest or deep learning, then you're going to see a lot of vertical stripes, because what model you're using is really determines the error that you see for a given observation. Or if you're in a world where actually really what's important is the families and the characteristics of the families, then you're going to see a lot of horizontal stripes, because basically all the models are not really that different, and what's really important is some families are hard to predict and some families are easy to predict. So we've made that heat map, and let me show it to you. So these are now sorted. So the sorted by the difficulty of predicting each unit, which is basically the average error averaged across all submissions. So what you see is for a very large number of families, all of the models predict their material hardship accurately. For a small number of the families, there's a huge amount of error. And that happens for all of the models. So if your idea is like, oh, if someone uses random forest, they can predict these kinds of families well, and if someone uses ridge regression, they can fit other kinds of kids well, that's just not happening. Basically, all the models are doing well with certain families and struggling with other families. And the variation across families, it dominates the variation across models. So if you were trying to say, I want to know what the prediction error is going to be for this kid with this model, you are much better knowing what kid it is than what model it is. Here's that heat map for all 6 of the outcomes. And again, you see a very common pattern. It's most clear in the binary outcomes, which are at the bottom, where basically a lot of the people are well predicted and some of the people are poorly predicted. And let me explain why this is happening. So basically what's happening is that most of the models are essentially predicting the mean of the training data. And so for cases where there's an eviction, if you predict the mean of the training data, you're going to be accurate for most people, because in this data set, most people didn't get evicted. Some people got evicted, and none of the models are anywhere close to predicting what's happening for those people. So that's why you see this very strong pattern that some people are very poorly predicted. It's those who are far from the mean of the training data. Yeah?
Are the same families consistently difficult to predict across different outcomes?
This is a great question. So let me repeat the question for people on the live stream. So is it the case that a family that's where the kid's GPA is hard to predict, is it also hard to predict the eviction for that kid? And the answer is generally no. So what we did is we calculated, but there's 3 exceptions. Okay. So what we did is we calculated the correlation between, so each given family can get a score for how difficult it is to predict that outcome for them by, again, taking the average of the prediction errors across models. So each family has 6 difficulty parameters, 1 for each outcome. And so then you can calculate the correlation of those difficulty parameters. And for most pairs of outcomes, the correlation is close to 0. So for example, if eviction is hard to predict, then it doesn't tell you anything about whether grit will be hard to predict for that family. Now there's 3 exceptions. First is there's a correlation between the difficulty of predicting eviction and material hardship. And so part of that is because eviction is part of the material hardship scale. So that's partially mechanical. The second is job loss. And the difficulty of predicting job loss is correlated with the difficulty of predicting eviction and the difficulty of predicting material hardship. So that could be because there's some outside variable, like let's say substance abuse, that might lead to job loss and eviction and material hardship. Or it could be that people who have unexpected job loss are then more likely to have unexpected eviction and material hardship. So we don't know exactly what the causality is. But so to summarize the answer, it is not the case that families who we struggle to predict one thing, we struggle to predict that other thing, but there is a weak correlation for some pairs of variables. Okay? So what do these results mean? So basically, I've just showed, everything I've shown you is just, that's true, that's what happened. What does it actually mean? It's much less clear. So I think there are a number of possible next questions. Is it possible to get better predictive performance for this data in this task? This is kind of a machine learning question. So like if we had used different techniques for data preparation, if we had used different techniques for statistical learning, if we had done this or that, is there some better way to do this? And if my personal guess is no. But if someone can do better, great. I would love to see how. Anyone who can do better, substantially better than what happened in the challenge, I want to know. I would love to read your paper. Like, that would be amazing. So I would love, love, love to be proved wrong. The second question is, why is the unpredictability so high, even using modern machine learning methods and what many social scientists would consider to be a large and high-quality data set? And so this is a question that we've been working on a lot already. There are a number of possible reasons. I think the ones we've thought about the most are, one, there's just not enough cases. So for example, the training data only had about 2,000 cases, and the outcome data was missing for about, it varies, but like a quarter to a third of the cases because people drop out of the study. So we have really only, roughly on the order of 1,500 examples for training. And so you might, someone that does machine learning, that doesn't sound like that much, especially when the number of predictors is very large. So one possibility is what, as a social scientist, we think of as a large data set is actually not large enough for these kind of predictive modeling techniques to work really well. So I said, Sarah, it's only 5,000 families. And she said, Matt, it's 5,000 families. So, I mean, I just do want to be clear that it is an enormous effort to follow these 5,000 families over these 20 years. But that may not be the scale that a lot of these techniques show their value on. Could be the measurement error in the existing variables, particularly the outcome variables. So a number of these outcome variables are measured with error. And so if there's error in the measurement, then that's going to kind of make a limit to the possibility that you could predict it. Because there's just, you might be able to predict the true thing, but then there's measurement error that's causing a lot of the error. It could be also that there are important unmeasured variables. This is the one that I personally think is most interesting. So Sarah and her colleagues have thought about this a lot, and they have measured an enormous number of things, but the world is a big and complicated place, and it's hard to think of everything sitting in your office. And so the question is, like, how can we find these important unmeasured variables? So we're calling this stuff dark matter. Kind of like in astronomy, there's this stuff out there. We know that it is doing stuff, but we don't really know what it is. And so we think here machine learning can be really helpful for helping us discover this dark matter by allowing us to target in-depth interviews with the families who are very hard to predict. So if we find people who are very hard to predict, those people potentially have a lot of this dark matter. So often if we think about how we do sampling for interviews, it would be kind of ad hoc. Or maybe if we thought we were being especially rigorous, we would do a random sample, simple random sample. But if we do a simple random sample, that's not going to find the kids that have the most dark matter. So if we use the predictions to help us find the kids that have the most dark matter and we learn from them, we're more likely to discover what that dark matter is. And so what we've been doing is going and interviewing the kids and parents from a number of these families. So I want to briefly explain the sampling design here because I think it's a good illustration of how machine learning methods can be very complementary to other techniques in the social sciences. So the x-axis here is the predicted GPA. The y-axis is the residual GPA, so the difference between the predicted GPA and the actual GPA. So people above the line are doing better than expected. People below the line are doing worse than expected. And so what we do is we split a challenge here is that there is a mechanical relationship between the predicted GPA and the residual. So for example, if you're predicted to have a 4.0, you can't be doing better than expected. And if you're predicted to have a 1.0, then you can be doing a lot better than expected, but not worse. And so if we just pick the kids with the biggest positive residuals and the lowest residuals, that would mean we are focusing our sample more on certain sub-ranges of the predicted values. So we split the predicted values into terciles, low, medium, and high. Then within each tercile, we took the kid that was most beating the odds and most struggling unexpectedly. Then we split the remaining kids into 3 terciles, better than expected, as expected, worse than expected, and then we randomly picked 1 kid from each of those terciles. So that's the sampling design that gives us 15 kids per city, and then we did that in 3 different cities. And so we've been conducting interviews with the kids and the parents to try to understand what these potentially unmeasured variables might be. And this is an example where we can have this process of continual improvement. We do systematic longitudinal data collection. Then we have a predictive modeling exercise. We find the people that are poorly predicted. We do in-depth interviews with those people. And then we improve the data collection for next year, so for the next wave. So right now there's going to be an age 22 wave of fragile families. And right now we are using the results of these interviews to help inform what the next wave of data collection should look like. And if we go through this cycle 100 times, we should be better at doing it than we are now. That's the hope. Questions? Oh, we have a lot of questions. All right, do you want to start passing the mic? Let me just, I'm actually like 1 slide away from the end, so let me just end and then we'll take the questions. So what's next? So we have 1 community paper that we're working on that will include all the codes and all the predictions that people submitted. So when people participate in the challenge, they don't just upload their predictions, they also upload their code and a narrative explanation of their modeling strategy. So those will all be open sourced as part of the community paper. And that can be then a data set that other people can use also for research. So we think about meta-analysis. We often analyze these higher level outputs of the scientific process, but here we can analyze much more of the raw materials. And that's possible because so much of this is standardized with a common task, a common data set, and a common metric. We have a special issue of the journal SICSS, which is a new open access journal from the American Sociological Association. All participants in the challenge had a chance to submit a manuscript describing their approach to the challenge. 12 of those will be published, and they will all be accompanied with code and a computing environment. So the idea is that people should be able to easily reproduce these results. And so not just what we learned during the challenge is the code alone is not enough. You also need the entire computing environment. So each of these will come with a Docker image, which has the necessary dependencies. We ran all of the computing on an Amazon EC2 so that everyone will have, as much as possible, everyone will have access to the same computing environment if they want to take these submissions and try to improve them or combine them or learn from them in some way. We have 3 papers from our group describing what we've learned in the process of doing this mass collaboration. So the first is the paper about the privacy and ethics audit. The second is the paper about improving the metadata infrastructure. That's a paper that Alex worked on and wrote. I will talk much more about that after the break because it illustrates some of the things that you'll experience as you start to work on the challenge yourself. And then the third is a paper about computational reproducibility. So as we tried to make the results in the journal computationally reproducible, we learned a lot. And this paper describes some of our successes and some of our struggles. So that's what's next. And what is immediately next is a coffee break, and then you'll get to work on the Fragile Families Challenge, but we have a few questions.
Just to clarify, am I right that the traditional sociological approach is to take some variables based on our just some theories and hypotheses and to test them, no matter how big is R square? And the second approach from data scientists is just to put everything in,
Yep.
no matter how interpretable is this, just to see how well it's predicted, right?
Yep, that's exactly right. I think that's a great description of two kind of extreme approaches. I would say one thing I would add to the sociological approach is to decide what to put in based on theory or domain expertise or knowledge. And the data science approach much more is let's let the data decide what should be in there and what should not. And so after the break, I'll talk to you about how people participated in the challenge, what techniques they used, and we'll show try to show some of the differences in the ways that different people from different communities approach the problem.
I'm sure you'll probably we'll see what variables are in there, but I wanted to know if you guys have variables about the way people look. So, you know, are they attractive? Are they not? How are their teeth? Do they have acne and other kind of really contextual features that have a huge effect on how people perceive them, whether it be teachers or employers or landlords, that would affect what their experiences are?
That's a great question. So I don't want to dump over my water. Okay, so these are the questionnaires from the Fragile Family Study. So I think this is great for illustrating something about the scale of the data collection. And I believe it's the case that there is nothing about physical appearance in here. Is that, Alex, do you know?
That sounds right to me too.
Okay. So I think this is a very important point because it illustrates something important, which is I think no matter how much data you collect, there's always more that you haven't thought of or didn't collect for some reason. I want to then a couple more specific things. So to make these predictions, we have data from when the kid is 9, and we're trying to make it when the kid is 15. So it could be the case that the kid's appearance, even if you knew what the kid looked like at age 9, that's not super relevant for what the kid looked like at age 15. But for the parents, perhaps what they looked like when the kid was 9 and the kid was 15 would be more similar. The other thing I want to say is for the purposes of prediction, it's not clear that we need to exactly measure the thing we care about if there's something else that is correlated with that. So I believe we do measure something related to they did measure something related to self-esteem, perhaps, of the kid. I would guess that's in here. And so if self-esteem is correlated with physical appearance, for the purpose of prediction alone, we don't care. So this is another big difference between data science approaches and social science approaches. So yeah, any other questions?
I'm curious why grit is framed as an outcome variable, given that it's kind of seen more as like a predictor of JPA and those kind of things. So how do you decide what is a predictor variable and what's an outcome variable?
Yep, I think that's a great question. So it's true that grit is often thought of as a predictor. We were curious about where grit comes from. Why are some kids more gritty than other kids? And so that is why we picked it. And then more generally, how did we pick these 6 outcomes? We wanted for the continuous ones, first let me say this is something we did in combination with the domain experts, so Sarah and the other PIs of this study, because we wanted to pick things where the predictions would potentially be meaningful and useful for scientific processes. And we also think of this actually just as the first step, and then we want to use these predictions for other things. So I told you about how we're using the predictions for interviews. We also want to use these predictions for other things. So that required us to think about what were some scientific goals we wanted to achieve, and then which variables would having good predictions of those help us achieve those goals. So for things like GPA and material hardship, we were very interested in kids and families that were doing much better than expected, beating the odds. Sarah has had a long interest in trying to find kids and families who are doing better than expected to try to understand what about them is allowing them to be successful. And then the flip side of that is the darker side of kids who are, and families who are doing much worse than expected. So if you have a family that appears to be on a good trajectory and then that falls into deep poverty, what was it that caused that family to spin out of control? And then obviously the next question would be, is there things that we can do to prevent that from happening? For the binary outcomes, we were thinking more about causal inference. So to what extent, if we can make an accurate prediction of whether someone will be evicted, then that could be used, one, to target interventions, but two, potentially could be used as something like a propensity score to try to estimate the effect of eviction. I do want to say, though, that turns out to be much more complicated than we had thought. So combining this kind of prediction and causal inference is subtle and hard. I think Justin Grimmer talked a little bit about the challenges of machine learning and causal inference. So we thought we were going to do that, and then we've run into some of the subtle and complex issues, and we're still working on that.
I'm thinking about doing ensemble learning after we receive several submissions. Ensemble learning is like doing the majority vote for the outcome of several algorithms. And as the organizer, you have received several good submissions, and maybe we can just do some weighted or average weight for their prediction, and maybe we could somehow have a better result. That's just my guess.
Absolutely. So I was super excited about that as well. I mean, when I started this project, I was very excited about ensemble learning techniques, and I was very excited about the idea that we could produce something together that was provably better than what any of us, even the best one of us, could do individually. So like this idea of the wisdom of the crowds, if we want to all estimate the weight of a certain, like the classic example is a cow, if we all make a guess and take the average, that's going to be better than even the best one of us individually. So to me, that's like a powerful and beautiful idea that by working together, we can do better than even the best of us can do individually. So I was hoping the ensemble would be better. We did an ensemble of the submissions, and it's basically the same. In some cases, it's even slightly worse, in part because, so I think there's a first order problem, and the first order problem is that all the submissions are basically the same. And so ensembling them together doesn't add a lot. Then you could say, well, ensembling, you could still add a little bit, and it's true, but then you have to still you have to have enough data to learn the right weights. And so when we try to add in the ensembling, we add uncertainty about learning the right weights between the different models. And so in some cases, we can even do slightly worse because we didn't do a good job enough of learning the weights. So a lot of the intuition about ensembling that I've seen comes from settings where there's enormous amounts of data and you can have a good job of learning the weights. I think this is not one of those settings. But again, the first order problem is that all the submissions are basically the same, and so two heads are only better than one if they have different stuff in them. Yep.
Hey, this is super interesting, especially the stuff about dark matter. I want to ask about some modeling choices. So if I understand correctly, this is the performance on the held map data set, right? And is this just trying to predict 15 from 9, or are you pooling the results from like 0 to 1 and 1 to 3?
So you get data from birth to year 9 to try to predict year 15.
Okay.
So you could use, so this is a choice. I mean, this is a choice that you all will get to make. So many people tried to use all of the data. Some people said, let's just use the year 9 data. Maybe there's not a lot of information in the older data. Or some people said, let's just use the data that we heard from the mother, for example. Or let's just try to use the data from the kid. So you could do whatever you want. You can use certain subsets of the data if you want. That's a choice that you all can make with your team. And given the amount of time that you have, it will be very difficult to clean and prepare all of the data for all the respondents from all time. But people in the challenge had access to all of it.
Got it.
Yep.
Did you, and I imagine you all played with outlier removal. I mean, it's some matter of violence to remove the most unpredictable families, and you probably don't want to do that, but I just wonder if that was attempted and if it was really changed things.
Yeah, so we could have done that, but we had a pre-specified error metric, which I think is an important part of this. So we said we are going to do the mean squared error on the holdout data. That's it. And so there's a very interesting paper by Jay Kaufman, Amit Sharma, and Duncan Watts, where they show if you change the outcome metric, you can, if not the outcome, but the slight variations in what the metric is and how you handle outliers, you can actually get what appears to be very different predictive performance. So even if, so the kind of ideas that we see with p-hacking and phishing and stuff, and we think predictive models aren't subject to that, that's not true at all. So I think it's definitely the case that there are these researcher degrees of freedom, even in predictive models. So this is one reason why I like the common task method, which is everybody is doing exactly the same thing. If we had picked a different error metric, we might get slightly different results, but I think the most important thing is that we're all doing the same thing, which makes things comparable.
Thanks.
And we have a few questions from our live stream. Adonar asks, just for some clarification on the GPA error heat map in the slides. Yeah, just pointing out the large. I think just I guess in the live stream I saw no red, only white.
Yes. Okay. So this is a live stream problem. Sorry about that. So Adonar is in Mexico, and he actually was a participant in the Fragile Families Challenge. He has a paper coming out in the special issue. And he was also a participant in the Summer Institute in 2017, where people did this while the challenge was actually happening. And some of them made it their second week project. And now they have a paper coming out in this special issue. So for people on the live stream, if it's hard to see the red, I apologize for that. The main pattern that you see here is that most families are predicted well by all of the models, and a few families are poorly predicted by all of the models.
Okay. And then David from our Boston site asks, are there measures for time and risk preferences either for kids or parents?
So the answer is, I don't think so. In all of this, I don't think there are measures for time and risk preferences, but we have I'll give you a little preview of what is going to come after the coffee break, which is this is a challenge, this is an issue that arose during the challenge where people wanted to know what is actually in all of this data that had been collected. And prior to the challenge, the documentation for the study was like this, in PDF files designed for people to read. So we could sit and read this and answer this question, but there wasn't a lot of documentation that was machine readable that was able for people to search through. And so one of the things we did is created that machine readable documentation and metadata, and that should make it much easier to answer these questions, and I'll teach you a little bit about how to use that after the break. But my short answer is I don't think it's in there. But there could be something correlated with it. So for example, there's a question about did you complete your tax return on time? Which in some of the models turned out to be apparently an important predictive variable. And so that could be measuring some kind of measure of, not exactly risk preference, but ability to stay on task in a very complicated thing. Any other questions? Okay, so what we're going to do is we're going to take a break. We'll come back here at 11, and we'll get started. I'll teach you how to do the challenge. Then you'll have the rest of the day to work on the challenge in your groups. So see everyone back in 10 minutes.